Okay, this is section 2.3. This is going to be part 1 of 2. And so this is, I'm going to go through examples 1 through 4. I'm going to start by talking about polynomials. Polynomials take on the form p of x or f of x or g of x or whatever. A x to the n plus a sub n minus 1, x to the n minus 1, etc. with descending order of powers. Keep in mind, again, as we talked about before, powers must be whole numbers. No negatives, no fractions, no decimals. The a's, the coefficients, can be we're only going to deal with ones with real numbers. You can have ones that are complex numbers, but we're not going to deal with those in this course. And they go to x to the first. Normally we don't write that first power. A to the 0, x to the 0. We also normally don't write the x to the 0 power. A, just plain A, is called the leading coefficient. A0 is called the constant term because x to the 0 is 1, so it just goes away. Okay. This is standard form, which is descending order of powers. We'll talk about a couple of graph transformations here. Example 1. So here we have g of x is 4x plus 1 cubed. That looks like it would be an x cubed function that I'm transforming. So I'm going to take my graph. And the cubic was one of our 12 basic functions. The basic quintic looks very similar. And it looks like this. So for transformations here, the minus 1 part, or the plus 1, means I go left 1. And 4 means I'm stretching it vertically 4. So I'm putting it over here. And I'm really exaggerating it. To be more stretched out. And the second one they give me, h of x, is a quartic. A quartic's going to look like a quadratic, roughly, a little bit flatter on the bottom and a little bit steeper on the sides. Not squared. I don't know why I wrote squared. It's supposed to be to the 4th. So this looks like an x to the 4th, which is going to look like, again, we're doing sketches. This is a flatter bottomed, sharper. It looks similar to a quadratic, but not quite. So my transformations here, right 2, up 5, and flip it upside down. So my purple one, I need to go one more up here. Right 2, up 5, open it down. Actually, what they showed in the book was negative x to the 4th before they shifted it. But either way, putting all the transformations into it to get it upside down, one that looks like this. You should be able to do that without the graphing calculator. Okay. So that's something I'd like everybody to learn how to do is make sure you know your 12 basic functions and how to do the transformations without the calculator, because that will show up on tests in a no calculator part. This part probably won't, but we're going to talk about combining a couple of graphs. This I don't normally expect you to do without a calculator, and we'll do but it's good to kind of have the basic ideas. So here I've got an x cubed and a plus x. Here I've got an x cubed and a negative x. So x cubed looks like this. Positive x is a line with a slope of 1. Negative x is a line with a slope of -1. So what am I doing? For the first one, I'm taking this one and I'm adding that one. Then we'll do x here. What is my result? Makes very little difference. Oops. Makes very little difference away from the middle, but my blue one should actually go through the origin. What does it do? I add them together and it just stretches it out a little bit. When I'm talking about something like 2 cubed is 8, I add 2 to it. That makes a little difference. When I'm talking about something like 4 cubed, 256, adding 4 doesn't make much of a difference. So x makes a little bit, stretches it out a little bit in the middle and not much on the sides. You can get a better picture looking at 201 in the textbook. This other one, we're going to look at our x cubed. And our negative x. So when I add these together, I actually get something inside of 1 and again, they've got a little bit better picture. So this is -1 and 1. Inside of there, I actually get this little part where it hooks down. Okay. And cubics tend to do that when we start subtracting powers that are below the term of the degree. The degree is a cubic. That really happens to all polynomials when I start subtracting things except quadratics. We start to get these little humps and hooks. Okay. The number of humps. Now, we can call a hump anytime we have one of these. This top one is a local max. They're called extrema. All of them are called extrema. The high ones are called maximums. Even though it's not the absolute maximum, it's a local maximum. Meaning it's a maximum between some smaller location. Within a region on both sides, it's the maximum. Here, this is a local min. The number of extrema is at most 1 less than your degree of your polynomial. So if I have a cubic, it's at most 2. I'll give you a hint, it's either 2 or 0. They always go in pairs. A quartic, that's 4th degree, could have 4 or 1. A 5th degree could have 4. No, a quartic could have 3 or 1. Sorry. Quartic being fourth degree has one less, at most 3. And we go down by groups of 2, so 3 or 1. A quintic, fifth degree, has at most 4, go down in 2s, 4, 2, 0 are my options. Sixth degree has at most 5, 5, 3, 1. So, looking at cubics, third degree. That is going to be something like ax cubed, and I don't care what's after it. If a is positive, I'm going to get something that looks like this. It has the following end behavior. I'm going to change this from a y, maybe. And I'm going to use limit notation for my end behavior. Limit as x approaches negative infinity. Is going to be negative infinity. Limit as x approaches positive infinity is going to positive infinity. Sometimes we'll call this end behavior down up, reading from left to right, down, over here on the left, down, and then up on the right. What's a negative cubic going to do? Well, it's going to flip it. It can be moved around however I want, but I get basically this. My end behavior just reverses. So now when I'm approaching negative infinity on the x, I go to infinity. My second one here is I approach positive infinity. I go to negative infinity, or I say up, down. Fifth degrees are going to follow the same thing. The only thing that's going to change in the general shape of the fifth degree is you may have more humps in here. Instead of 2, you might have 4. Or you might still only have 2. It's a possibility. Okay. But because of fifth degree, it could be 4. There could also be some variance in the shapes there, which we'll talk about later. Okay. Quartics. Say f of x here equals ax to the fourth, and something comes after it. Quartics, remember, can have 3 humps. They can look something like this. Those could be symmetrical. You could end up with one that's this, or one that's more like this. All of those are different options for quartics where a is positive. My end behavior on this quartic, both of them are going up. So as limit as x approaches negative infinity of my quartic is infinity. And as it approaches positive infinity, it's still infinity. Now, as I go down, what changes? As a is less than 0, it opens down. Again, I've got all the options for shapes, but they're all opening down. All the options for shapes I gave them a upward opening one. And both of my end behaviors are down, down, or I can think of this as both end behaviors are approaching negative infinity. Let's make that a little more clear. Both end behaviors approach negative infinity. So we're going to take a look at a couple of different polynomials on the graphing calculator. I don't know what that scribble is, but let's get rid of it. Okay. And we're going to look at what happens to them as I change my zoom. Okay. So these are the ones in example 3. The first one I'm going to do is x cubed. Oops. I'm going to have to clear this whole line. And then I'm going to have x cubed minus, oops, got to get out of the exponent first, minus 4x squared minus 5x minus 3. And I'm going to set my window exactly how they do it in the book. If you look, they say negative 7, 7. That means the x coordinates. And then the y is the second by negative 25, 25 is y. So y min is negative 25, y max is 25. Probably make my scale 5 here. And I'll graph it. We can see these graphs look pretty different. Okay, the second cubic with the minus 4x squared minus 5x minus 3 really drops down. Well, we're going to take a look at what happens when I zoom out some. Now, we're not going to zoom out the x's a ton because cubics grow really quickly. The y's, we're going to go to negative 200 to 200. I'm going to go by 20s. Again, I go somewhere between a 10th and a 20th, my area, my space for the scale. So basically I took 1 0 off there. Now they look closer. You can still tell a significant difference between the red and the blue. Now we're going to go way out. And we're going negative 56 to 56. I'm using the actual zooms that they show in the book. And 1,000, 12,800. I'm going to go by 1,000. I think that'll be fine without zooming too bad. Oops, I didn't change my X scale. They start to look very, very similar here. Change my X scale to 5s. So it's a little less crunched in there. We get something that looks pretty similar on the graphs. They're not exactly the same. My end behavior for both of them, f of x and g of x, is negative infinity as x approaches negative infinity, and positive infinity as it approaches positive infinity. Okay? We're going to talk about a couple more. When you're doing end behavior, I always recommend being a little bit zoomed out if you're graphing, because you'll usually use the graphing calculator. But I always, recommend doing the graphing calculator and graphing it, and then being kind of zoomed out. Oops, not x to the 33rd. That's going to be a little high. So I'm going to example 4. I'm entering part A. That's not the key I want. Let's see if it's more zoomed out than I probably really needed to be. But it gives me the idea on end behavior. And I don't need to be more zoomed in. Limit, as this one was f of x. So x approaches negative infinity of f of x. I can see that it's going down over here. So that's negative infinity. And I can see that it's going up over here, positive infinity. Now let's do g of x. So I have an extra x here. I'm going to hit delete. We'll get rid of it for me. So there's the delete button on your calculator. It'll delete right over whatever you have. I don't know. I don't want to be there. I guess the parentheses is fine. That should be a plus. I don't know what I pressed that ended up like that. But plus 2x cubed, and this is example 4, the g of x function. I'm gonna make my window a little smaller this time. It's kind of huge. And here I can see, again, I'm looking at end behavior. So x approaches negative infinity. G of x is going up to positive infinity. As x approaches positive infinity, g of x is still going up, is also going up again to positive infinity. Okay, that is part 1.